Welcome to the deep dive. We're skipping the usual headlines today and going straight into something pretty groundbreaking. Intellect-2. Now, this isn't just another LLM. It's a 32 billion parameter model, sure, but the way it was trained, that's the real story. We're talking globally decentralized reinforcement learning.
Yeah, it's a big shift. Think moving away from those giant centralized compute clusters we usually associate with training these huge models.
Exactly. And from an academic standpoint, this is quite significant, wouldn't you say?
Oh, absolutely. Intellect-2's core contribution, academically speaking, is showing that you can scale reinforcement learning for frontier models using this kind of distributed permissionless network. It really questions that need for massive co-located hardware.
Right. It opens up different avenues for who can even do this kind of research and development.
Fundamentally new possibilities, yes.
Okay, so that's our mission for you today. We want to really dissect the key innovations here, get into the academics of Intellect-2, and focus on what makes this approach so unique. How is it pushing boundaries? We're working from the technical report on Intellect-2, and I've got some notes here from May 13th that pull out some key technical bits, especially the novel stuff.
Good.
And here with me is our expert co-host to give us that deeper analysis. We want to understand the what, definitely, but also the why and the implications of these innovations.
Happy to dive in. It's fascinating work.
Great. So let's start with the absolute core idea, the central innovation.
Right. So the big academic headline is definitely the successful use of reinforcement learning on a 32B model, but done across this globally distributed permissionless network. Random contributors potentially.
Not a single controlled data center.
Exactly. It's a major departure from traditional centralized RL training, which, as you know, relies on those tightly coupled high bandwidth GPU setups. Intellect-2 basically proves you can potentially use a much more dynamic, varied pool of compute resources from all over.
Okay, so conceptually, that's huge, but practically coordinating that. For RL training, which needs a lot of back and forth, how did they, pull that off?
Well, the linchpin is really their infrastructure, a set of new tools they built, and crucially, the asynchronous nature of their RL approach.
Asynchronous. Okay, unpack that a bit.
So, unlike synchronous RL, where everything kind of moves in lockstep agents, the parameter server asynchronous RL allows them to decouple things, generating the experience data, actually training the model, broadcasting the updated weights. These can happen somewhat independently.
So not everyone needs to wait for everyone else.
Precisely. And this is mainly managed by a framework they built called Prime-RL.
Prime RL. Got it. So this framework is the backbone. What's special about its design for this decentralized world?
It's a purpose built for this exact scenario, asynchronous distributed RL. The key architectural idea is separating the experience generation, the rollouts from the model parameter updates. They function as independent processes.
Okay.
They mainly communicate by exchanging training data and these model checkpoints. This design avoids needing a single central point managing everything in real time. And critically, it means the system can handle the kind of delays, the latency you'd expect when sending data globally.
Right. Network lag is unavoidable.
Exactly. Think of it like different teams collecting data and analyzing it separately, then just periodically syncing up to update the main plan.
That makes sense. So Prime RL handles the async flow, but you mentioned checkpoints, model weights. For a 32 billion parameter model, those files are enormous. How do you push those out efficiently and reliably across this kind of network?
Yeah, that's a huge practical hurdle. And that's where another piece of their infrastructure comes in, SHARDCAST.
SHARDCAST, okay.
SHARDCAST is their custom library for broadcasting these really large policy weight files, tens of gigabytes potentially out to all the decentralized workers doing the inference part.
How does it work?
It uses an HTTP-based tree topology, sort of like a specialized content delivery network, but just for model weights. The clever part is it shards the big files into smaller pieces.
Breaks them up.
Right, and it streams these shards in a pipelined way, so the workers can start downloading and rebuilding the model even while the full checkpoint is still making its way through the network. It cuts down the effective wait times significantly.
That is clever, like getting parts of a huge download early. Okay, but we're in a permissionless environment here. Anyone could potentially join. How do you trust the work being done? How do you verify the inference?
Another critical piece that's handled by Toplock.
Toplock.
It's their novel scheme for trustless, verifiable inference based on locality-sensitive hashing. Toplock lets trusted validators check if the rollouts, the data generated by the inference workers are correct.
How? Without rerunning everything?
Exactly. It works by having the inference workers generate these compact cryptographic commitments to the model's final hidden states during inference. Validators can then just recompute those specific activations, which is much faster, and compare them to the commitments.
Faster by how much?
up to 100 times faster than doing the full inference again.
Wow.
So it allows for rapid checks for any tampering or even just unintentional errors from different hardware setups. It's crucial for ensuring the training data is trustworthy in this open network.
Okay, so a fast cryptographic audit. That's impressive. So we have prime RL for async, SHARDCAST for distribution, Toplock for verification. How do these pieces actually work together? What coordinates them?
They're all brought together and managed by the Prime Intellect protocol. Think of this as the overarching decentralized orchestration layer for the whole network.
The conductor of the orchestra.
Sort of, yeah. It's modular, handles node registration, task distribution, result verification. It uses a decentralized ledger to keep track of training progress, data, contributions. It defines the roles, inference workers, Toplock validators, the actual GRPO training workers. An orchestrator component uses the ledger info to assign tasks to available verified nodes.
It's a really comprehensive system they've built. Okay, let's shift gears a bit to the training itself. RL, especially at this scale, can be notoriously unstable. What did they do differently in the training recipe to keep a 32 billion parameter model stable in this setup?
Yeah, stability is always a major challenge. They introduced several key things. One really notable innovation is what they call two-sided GRPO clipping.
Okay, GRPO is the RL algorithm, like PPO. What's standard clipping and what's two-sided?
Right. Standard GRPO or PPO clipping puts a limit on how much the probability ratio, new policy probability divided by old policy probability can change. This helps prevent excessively large updates, but they found a limitation.
Which was?
For actions that turned out badly actions with negative advantages, the standard clipping didn't apply an upper bound in the same way. This could lead to huge loss values from those negative examples, destabilizing the gradients, especially with big models.
Ah, okay.
So they introduced a new hyperparameter, delta, specifically to put an upper bound on that probability ratio even for negative advantages. This two-sided approach was apparently crucial for keeping the 32B model training stable.
That sounds like a subtle but really important tweak to the core algorithm. What else did they do for stability?
They also used data filtering both offline and online. Offline, before the main RL run, they used a smaller model, DeepSeek R1 Distill Q Quen 7B, to test their big data set.
To pre-screen the problems.
Exactly. They filtered out problems that were way too easy for the small model or ones that were just impossibly hard. The idea was to focus the expensive RL training on the problems where it could actually learn something useful.
Makes sense. Concentrate the effort and online filtering.
Online, during training, they made sure the GRPO updates were mainly focused on samples that actually showed some advantage, where some actions were clearly better than others. They'd keep generating rollouts for a problem until they got a batch with non-zero advantages, basically ensuring a stronger learning signal.
So better data selection overall. Did they monitor specific things during the runs as like early warning signs of trouble?
They did. Based on smaller experiments, they identified a couple of key indicators. One was the gradient norm starting to climb steadily, just a persistent upward trend.
Before things blew up.
Often, yes. So as a countermeasure, they used quite aggressive gradient clipping, sometimes setting the threshold really low, like 0.05 or zero point 0.1, just to keep those gradients in check.
Okay. Any other signs?
They also saw a pattern in the entropy loss. Normally, entropy decreases as the model learns, becomes more confident, but they noticed that sometimes before instability hit, the entropy would start increasing again after its initial drop.
Interesting. Like the model was getting confused again.
Something like that. That inflection point became another warning sign. Oh, and they also ran into stability problems just using PyTorch's torch.com pile optimization.
Really?
Yeah, so they ended up disabling it for the main runs just to be safe. It shows how sensitive these things can be.
Wow. Sounds like they are really walking a tightrope. Now, the model has a 32K context window, which is massive. How did they handle efficiency there, given sequences wouldn't always be that long?
Right, you'd have a lot of wasted computation with padding otherwise. They used sequence packing.
Packing.
Yeah, basically concatenating multiple shorter sequences together into one long sequence for processing, but using attention masks so the model still treats each original sequence independently.
Ah, okay.
The key thing for RL was ensuring that even though they were packed for efficiency, the actual learning updates still operated on complete individual samples. It just made better use of the compute resources.
Makes sense. Okay, so we've covered the architecture, the scalability tricks. What were the actual results? Did it work? What did they learn?
So INTELLECT-2 is based on QWQ32B, trained with their modified GPO. They ran two main experiments, target short and target long, basically varying the target length for a length-based reward signal.
Right.
A big success was managing the communication overhead. The SHARDCAST broadcast took about 14 minutes on average, but they successfully overlapped this with computation on the workers. They hit a pretty decent bandwidth throughput too, around 590 millidears.
So the async approach paid off there.
It seems so. In terms of timing, new model weights were ready for bashing in about 22 minutes for target short, maybe 29 minutes for target long. And interestingly, the compute ratio was about 1 part training FOPS to 4.5 parts inference FOPS.
So most of the work was happening out on the decentralized inference nodes.
Exactly. The training nodes themselves were kept busy, not much idle time.
And the model itself, did it get better at reasoning?
Yes, they saw clear improvements in task rewards during both runs, especially on math and coding problems in their test sets. So the reasoning did improve.
But at sense of what?
Well, the length penalty part, it did decrease, meaning the model got somewhat better at being concise when asked, but it learned this slower than in their smaller tests. It suggests the model didn't fully master sticking to the requested thinking budget within the training time.
Okay, so progress, but maybe not complete convergence on all aspects. How did it stack up against the base model?
Compared to QWQ32B, it performed better on math and coding benchmarks, which aligns with the training focus, but it slightly dipped on IFEVOL, which tests instruction following. Again, likely due to the specific training data and rewards.
Fair enough.
They also had an interesting hypothesis. Because the QWQ32B base model had already undergone some RL training before they started, it might have actually made it less stable for the subsequent decentralized RL fine-tuning.
Huh. Like RL training makes it more brittle somehow.
Potentially. Or maybe just harder to fine-tune further with RL. It's an interesting thought compared to starting with a base model without prior RL.
Definitely something to keep in mind. Okay, let's zoom out. The big picture significance of doing this decentrally at this scale.
Well, the authors argue this decentralized approach fits really well with this idea of test time compute scaling.
Where you give the model more thinking time at inference.
Right. They argue decentralized training is suited for that because scaling compute at test time reduces the need for tight coordination and shifts the burden to inference, which is easier to distribute. And as we said, the async RL helps hide the communication latency. Also, as models get more complex and do more reasoning, inference itself uses more compute and memory. Decentralization could be a way to handle those memory limits by spreading the inference load.
So it potentially unlocks scaling in a different way than just building bigger data centers.
That seems to be the implication, yes.
It really does feel like a potential turning point. Okay, to wrap up our deep dive then, can you just quickly summarize the core innovations of INTELLECT-2 again?
Sure. First, the headline achievement, demonstrating globally decentralized RL training for a 32B parameter model. That's new.
Right.
Second, the enabling infrastructure. Prime RL for the asynchronous coordination, SHARDCAST for efficient weight distribution, Toplock for trustless verification, and the Prime Intellect protocol tying it all together.
The toolkit.
Exactly. And third, the crucial training recipe modifications, the two-sided GRPO clipping for stability, and the smart data filtering strategies. These were essential to make it work at scale in this challenging environment.
And the wider potential.
It suggests a viable path towards more open source frontier AI models. It could democratize large scale training by reducing reliance on massive centralized resources. And importantly, they've open sourced the model, the code for Prime AMRL, and the protocol.
Where can people find those?
The model is on Hugging Face under Prime Intellect INTELLECT-2. The code is on GitHub, Prime Intellect A Prime ARL, and Prime Intellect A Prime Intellect protocol.
Great. This has been incredibly illuminating. Really appreciate you breaking down this complex work.
My pleasure. It's exciting stuff.
Absolutely. And for you, the listener, here's something to chew on. If AI development can be truly globally distributed like this, how does that change things? Who gets to build advanced AI? Who benefits? What new kinds of collaboration or maybe even new challenges arise when innovation itself becomes decentralized? It's a big shift to think about. Definitely check out those open source resources if you want to dig deeper. Until our next deep dive.